Hi everyone, my name is Daniel and I'll be presenting our perceptual loss for robust unsupervised homography estimation paper. Given a pinhole camera model assumption, a homography relates any two images of the same planar surface in space or any two images produced by pure rotational movement of the camera. One image, called a source, can be transformed by a 3x3 homography matrix H as if viewed from the viewpoint of the other image, called target. Traditionally, homography estimation was performed using non-learnable approaches, either in pixel space, like direct methods, or in handcrafted feature space, feature-based methods. Feature-based methods usually perform better than direct methods. However, their success depends on the quality of the handcrafted stages and the content of the image itself. Poorly distributed features, illumination variations, or large viewpoint differences are challenging for both direct and feature-based methods. Recently, with the advancement in deep neural networks, the town proposed a simple CNN architecture trained in an end-to-end fashion. The idea was to directly regress the parameters of a homography, and it achieved similar performance to traditional feature-based methods. A more effective approach is presented by Zeng, where the problem was formulated as per-pixel offset regression. However, supervised methods are often unlikely to be used in real-life scenarios, where ground truth homography labeling is prohibitively expensive. To mitigate this issue, Nguyen introduced an end-to-end unsupervised approach. First, a homography is estimated using both input images, and then homography estimation is learned by comparing the per-pixel intensity of warped source image and target image. Models trained using this formulation perform surprisingly well, even for images with big viewpoint differences. However, they are not robust to big illumination changes and cannot be used in real-life scenarios. In contrast, Zhang, by learning the feature representation used for both homography estimation and image comparison, achieved robustness to different lighting conditions, but not for images with big viewpoint changes. Therefore, robust unsupervised homography estimation for both big illumination and viewpoint changes at the same time is still an open problem. Here, we present a novel unsupervised framework for robust homography estimation. We propose to decouple learning representation for both homography estimation and image comparison by using a dedicated loss network to compare warped source image and target image. The homography is learned implicitly by comparing the images in feature space produced by the loss network. Extensive evaluation shows that such a formulation yields models robust both to viewpoint and illumination change. Since the homography should be invertible, we compare warped source and target images and swap their loss. Therefore, we call our loss function bidirectional implicit homography estimation, BiHomi loss. Our contributions are as follows. We introduced a new perceptual loss, BiHomi, to be used in unsupervised setting, which decouples homography estimation from representation learning for image comparison. We propose to use an additional photometric distortion step in the synthetic COCO dataset generation to evaluate the robustness of homography estimation to big illumination and viewpoint changes, which is more aligned with real-life scenarios. We achieve state-of-the-art performance using BiHomi loss on both SCOCO and PDS-COCO datasets for unsupervised homography estimation. Our framework is composed of two components: The first is the homography estimation network F, which can be realized by any architecture able to produce transformation matrix HST. In the second part of the pipeline, homography HST, estimated by hand, is used to transform source image IS into IS prime. Rather than directly minimizing only the distance between IT and IS prime, we encourage the network to simultaneously push IT away from the original IS in triplet fashion, additionally normalized by visibility mask M. The loss is highly inspired by Zhang, but instead of learning the feature space to compare images, we rely on perceptual similarity of high-level features extracted from pre-trained loss network, in example ResNet34. We can additionally repeat the procedure for swapped inputs, so that the final bihomi loss is a composition of ihomi losses in both directions and a regularization term that forces homographies to be invertible. Homography estimation is often trained and tested on the synthetic COCO dataset introduced by the tone. However, it does not model photometric distortion present in real-world images, such as contrast, brightness, and saturation changes. Therefore, we propose to use an additional data augmentation step in the synthetic COCO dataset generation, where we artificially model illumination changes by utilizing photometric distortion techniques used in SSD object detector. The first step involves randomly adjusting the brightness of the image. Next, random contrast, saturation, and hue noise is applied, and finally, the color channels of the image are randomly swapped with a probability of 0.5. Such a photometric distortion procedure is applied to the original image independently to create source and target candidates. The rest of the procedure is the same as for S-COCO dataset generation. We implemented 4 previously mentioned methods in PyTorch and Cornea. We modified the hand architectures to use a ResNet34-like feature extractor to make sure the performance difference between methods comes from better design instead of a better CNN backbone. All methods are trained using the Adam optimizer with a batch size of 64 and for 90k iterations. The initial learning rate is decayed by a factor of 10 every 30k iterations. We use ResNet34 as a fixed loss network G, with features taken after the first residual block. The homography estimation quality is reported using mean absolute corner error. We report the mean and standard deviation of 3 runs. Current unsupervised approaches give slightly worse performance compared to supervised methods on S-COCO. However, when both illumination and viewpoint changes are introduced, no unsupervised method can converge. Our bihomi loss achieves comparable or better homography estimation performance than supervised methods on both S-COCO and PDS-COCO for any of the tested backbones. We can use the S-COCO dataset and simulate different conditions by 2 parameters: viewpoint change ρ and illumination change delta. Viewpoint change ρ defines the maximum range of corner perturbation, and illumination change delta describes how strong photometric distortion will be applied to the image. The bigger ρ, the more viewpoint change, and respectively, the bigger delta, the more illumination change between input images. Now, the method of Nguyen, based on photometric loss, is robust to big viewpoint changes, but is not able to produce any reasonable model for big illumination distortion. On the other hand, Zhang's method is highly robust to illumination change, but only for small viewpoint change. Our Bahram loss is robust both to big illumination and viewpoint changes at the same time. We also want to find out how important is freezing the loss network for effective homography estimation learning. As shown in table, fixed loss network performs better. One of the possible reasons is that freezing weights of G allows using a bigger learning rate, which can result in better convergence. But even for the same learning rate, freezing the loss network is still a preferable policy. One of the shortcomings of using models pre-trained on the ImageNet is possible suboptimal results on out-of-distribution datasets. To test this vulnerability, we compare Zhang method with the original and our Bahram loss on a FLIR thermal dataset, preprocessed similar to SCOCO. Although thermal images are vastly different than color images the loss network was trained on, our Bahram loss still achieves better performance. Please take a look on our paper for more ablation studies and use cases. To conclude, we presented an unsupervised approach to homography estimation that is robust to big illumination and viewpoint changes at the same time. We showed that disentangling the homography estimation from representation learning provides better estimates. We also proposed to use an additional photometric distortion step in the synthetic COCO dataset generation and encourage future works to use it as a new evaluation benchmark of robust homography estimation. Then we presented a study of modern homography estimation baselines along with our bidirectional implicit homography estimation Bahram loss on both SCOCO and PDS-COCO. Bahram achieves a new state-of-the-art performance for unsupervised homography estimation, which is also comparable or better compared to supervised approaches. Thank you all for watching.